Uh, okay. So I'm recording this video. So this lecture is the last lecture in this course. So in this lecture, so I will briefly introduce about the parallel process architecture of a computer system. So actually, until this time, we learned about in chapter one, so we learned about the performance, the how to measure the performance of a computer system. And then in chapter 2, we learned about the instruction set architecture. Then what is an instruction set architecture? So ISA, the instruction architecture, is an interface between software and hardware. Okay, so in the software programmers write a high-level language code, and then this high-level language code is translated into instructions, right? The machine instructions. And then in the instruction set architecture, we define the output, the output result of instructions. Then we can design the hardware based on the instruction set architecture. And then in chapter 4, we learned about the processor architecture, right? So actually we focus on this hardware architecture of a computer system. So we learned about the CPU, the hardware, the processor architecture in chapter 4. So we learned about the single cycle processor architecture and the pipeline processor architecture. And then in chapter 5, what did we learn? We learned about the memory system. So we learned that the memory systems are connected to CPU, and then the memory system provides the data required by instructions. Okay, so also we learned that in order to improve the performance, so we organize memory hierarchy, and then also we learned about the virtual memory, right? The virtual memory concept. So actually, until this chapter 5, we focused on we were focused on the single core architecture. Okay, so it is composed of one CPU and memory hierarchy connected to this one CPU. And then actually this CPU is usually called a core. Okay, and then so what is a parallel architecture? The parallel architecture means that we can learn multiple thread or multiple processes concurrently. So what does that mean? We can run multiple threads at the same time. Okay. So this is the parallel execution. And then parallel architecture, with parallel architecture, we can implement parallel execution of multiple thread. Okay. So in chapter 6, we will briefly learn about this parallel processing and parallel architecture. Okay, so then what is the parallel architecture? So as I mentioned, that everyone wants good a good computer system. So what does that mean? A good computer system represents the computer system which can exhibit higher performance. But we learned about the performance metric in chapter 1. So what are those? Latency and throughput, right? So what is the latency? What is the latency of a computer system? So this is the execution time of a single thread, right? It's a latency. But we can also improve the performance of a computer system. So which means we can improve the throughput, the amount of workload which can be done in a unit time. So this is the definition of throughput, right? Throughput. So, so throughput is the amount of workload done in a unit time. Then how can we improve the throughput of a computer system? So we can improve the amount of workload, right? The amount of work. Then how? We can increase the processors, right? So in a real world, in order to improve the performance of a group or a company, then we can hire more workers, right? We can increase the number of workers. So by doing this, we can improve the performance of a company. So it's the same. It's the same to the computer system. In order to improve the performance, so which means in order to improve the throughput, throughput of a computer system, we can implement parallel architecture. Then, which means we can implement the multi-processors or multi-cores. Okay, so so by implementing multi-processors, so which include multiple CPUs, we can improve throughput, the throughput of a computer system. So this is the very typical approach, right? So as I mentioned, in the real world, to improve the performance of a company, then we can improve the number of workers, right? And then computer systems, to improve the throughput or performance of a computer system, then we can increase the number of CPUs or number of cores. So this approach or this architecture is called a multiprocessor architecture. So multiprocessor. Okay. So and then we can exploit the multiprocessor architecture with multiple thread. So what does that mean? If there are multiple independent jobs or multiple independent tasks, then we can exploit, where we can utilize the multiple processors or multiple cores. Okay, so the parallel process architecture. So in order to exploit the parallel process architecture, then we can have multiple tasks, and then these multiple tasks can be executed concurrently by multiple CPUs, right? So then we can achieve high throughput, okay? High throughput for independent jobs or tasks, right? So this is called the task level parallelism. So parallelism represents some parallelized uh, parallelized work. Okay, so it's in Korean. It can be called 병렬화, right? So so the parallelism means that some this one. So parallelism means that something can be parallelized, right? So task level parallelism means that tasks can be parallelized. So using the multiprocess architecture, we can implement task level parallelism. So which means using multiple CPUs, we can run multiple tasks concurrently, okay, in parallel, okay? Then how can we improve the performance of our application? So in order to improve the throughput of our application using the parallel process architecture, then we need to implement the parallel program. Okay, so it means the single application. So this is the single application. Then, but the single application can generate the multiple thread. Okay, multiple thread, and then so these multiple threads can be independently executed by multiple processors. Okay, so which means in order to utilize the parallel process architecture, then we need to uh, we need to design parallel programs. Okay, so let's learn about some parallel hardware and parallel software. So this is the example of parallel hardware. So firstly, we can think about the serial hardware. So that is so what we have learned at this until the chapter 5. Okay, so we just assume a computer system includes a processor, a single CPU, and memory hierarchy, right? Like this model, the CPU and memory. So this is the memory hierarchy. So example of this serial hardware is the Pentium 4. So this is very old CPU, right? So Pentium 4 just includes a single core CPU. So which means there is only one CPU in a chip, and then this one CPU is connected to the memory hierarchy. Okay, so and then this is the CPU chip. So this is the serial hardware, and then the example of parallel hardware is the quad core Xeon. So this is the also very old Xeon CPU. So Xeon CPU is the brand name of the server Intel server CPU, right? And then the modern Xeon CPUs include 20s or 30s, around the 30 cores in a chip. But this is a very old Xeon CPU. So, but as you can see, you can observe it's quad core Xeon. So what is quad core? It means that there are 4 cores. So which means 4 CPUs in a chip. So 4 cores. So because there are multiple cores in a single chip, these multiple cores can execute multiple thread concurrently. Okay, this is an example of parallel hardware. Okay, so also we can observe the example of sequential software and concurrent software. So what is a sequential software? So this is so one thread. So the application just generate only one thread, and then this one thread is sequentially executed by CPU. So this is the sequential software. Then the matrix multiplication. So we can also uh, think about the very simple computation kernel, such as the matrix multiplication that generate only single thread. Okay, and then so if we use some parallel programming API such as pthread, then we can also generate the multiple thread from a single software. But in this example, so this matrix multiplication kernel can just generate only one thread. So this is the example of sequential. So sequential software. So which means that the instructions are sequentially executed. And then also we can observe concurrent software. So concurrent software means that for the single application, this single application can generate multiple thread. Okay, and then these multiple threads can be executed concurrently. Okay, so example is the operating system, but the modern applications. So so actually the modern computer systems equip the multi-core CPUs, right? And then in order to exploit these multi-core CPUs, then application needs to generate multiple thread. So which means modern applications usually create multiple thread, right? So for example, the web browser such as Chrome. So the Chrome creates multiple processes or multiple thread. So which means even though we just launch one application, then this single application can create multiple thread, then multiple thread can be executed by multiple cores concurrently. So this is the example of concurrent software. Okay, only so actually in a multi-core architecture, we can also learn sequential software or concurrent software, right? So actually, in order to exploit, in order to utilize the parallel architecture efficiently, then we need to build our applications also effectively for parallel architecture. Okay, so this is the challenge of parallel programming. Okay, okay, so let's see the example of parallel programming. Okay, so what is the parallel programming? So when you learned about some uh, instructions in chapter 2, we just focus on the single-threaded program, okay, which means that a program just creates the a single thread, right? But as I mentioned, in order to utilize parallel processor architectures, then an application needs to create multiple thread. So which means that it's a parallelizable thread. Okay. So parallel software is the problem. So which means, so actually, so this single application needs to be parallelized. Then it should be executed by the multiple cores. So parallel programming is not easy. Okay, so think about this. For example, the matrix multiplication, the A multiplied by B equals C. So actually, for the matrix multiplication, so we are familiar with the sequential programming. So what does that mean? In order to build the matrix multiplication kernel, then we can just generate the high-level language code using iterative loop, right? And then this iterative loop is executed sequentially, right? So we are very familiar with the sequential programming. So which means an application just generate only one thread, and then this one thread is executed from top to bottom. So this is the sequential software, right? So we are very familiar with this sequential software model. That's what we have learned until this chapter 5. But in order to utilize the parallel processor architecture, so as I mentioned, so a single application needs to create multiple concurrent thread. Okay, So, and then for this programming model, so this programming model is not easy, right? So actually, we need to implement the parallel algorithms, okay? In order to implement this the parallel programming model, then we need to also implement the parallel algorithm. But the parallel algorithm is much more difficult than sequential programs. Okay, so this is the problem. Okay, okay. So then let's learn about the Amdahl's law. So Amdahl's law explains the peak performance, by the parallel processors or parallel architecture. Also, Amdahl's law explains the sequential part. The sequential part of an application can limit the speed up of parallel processors. So this is the Amdahl's law. So let's see the example. So actually this is the application. Okay, so this is the application, right? But when you analyze the application, then we can divide this application into two parts. So it's the sequential part. Firstly, the application includes the sequential part. Okay, what does it mean? This part needs to be executed sequentially. So which means the sequential part cannot be parallelized. Then also we can observe the parallelizable part. So which means that this part can be parallelized. So parallelized. So using for this part, we can create multiple thread. Okay, and then this can create multiple concurrent thread. So this is the parallelizable part. So parallelizable part can be executed by multiple cores in parallel. So which means actually if we just apply parallel process architecture, only this part, the parallelizable part can be improved. Obviously, right? Obviously, right? So we can calculate like this. So this is the example. So let us assume that our computer system includes 100 processors, right? And then we want to achieve 90 times of speed up. Then what is the fraction of parallelizable part for to achieve the 90 times of speed up? So if you see that this configuration, so it means that, oh, our computer system includes 100 processors. Then what is the expected speed up? What is the expected speed up of this computer system? So it is because, so because there are 100 processors, so compared to the single core uh, processor, then we can expect that, oh, this computer system, we can achieve 100 times of speed up. But so in this example, so we want to achieve the 90 times of speed up. So as I mentioned, we can split a single task into the sequential part and then parallelizable part. So this is the execution time of the sequential part. So it is called the T sequential. And then also we can define the execution time of T parallelizable. So this is the execution time of parallelizable part by a single core CPU. So using the 100 processors, we can reduce the execution time of T parallelizable divided by 100. Right, because this is the parallelizable part. So we assume that the parallelizable part can be parallelized the infinitely. Okay, so this is the new execution time. So then actually we can say T sequential is the 1 minus T parallelizable, right? So we can calculate the speed up like this. So this is the baseline, the execution time of the single core, and then the sequential part, so 1 minus T parallelizable. So this fraction is is, is the same. So because even though we apply 100 processors, this part cannot be parallelized, right? And then the parallelizable part can be reduced. Okay, so it's just divided by 100 because there are 100 processors. Only this part can be reduced. Then the speed up is 90. Then if we just solve this equation, then the fraction of parallelizable is 0.999. So what does that mean? If our application includes the 99.9% of parallelizable part, then using this processor configuration, we can achieve 90 times of speed up. Okay, so 99.9% of parallelizable part. Okay, so which means it's nearly 100, but the speed up is only 90 times. Okay, but our expectation is 100 times, but it's limited by actually this part. It's a sequential part, right? This is what Amdahl's law uh, says to us. Okay, so that's what Amdahl's law explains. Okay, so actually the speed up of a parallel processor is limited by the sequential part. Okay, so because only 0.1% of sequential part just limit the 90 times of speed up. Okay, so we can just achieve 90 times of speed up. Okay, so this is an example. Okay, so let us assume that our workload is composed of 10 scalars. So which means that this is the sequential part. Okay, this is the sequential part. And then 10 by 10 matrix sum. So which means it's the A plus B equals C. So these are matrices. So we only know that for the matrix sum, we can perform the element by element addition, right? So which means the matrix sum can be parallelized. So this part is the parallelizable part, right? And then we can just calculate the speed up from 10 to 100 processors, right? So scalar is the sequential operation. So using and then this is a sum of 10 scalars. So we just assume that the execution time of this sum is the T add. Okay, so using a single processor, then execution time is the 10, and then also 10 by 10 matrix, there are 100 elements, and then we just perform the sequential addition, right? So T add. So this is the total execution time for a single processor. Then let us assume that we can apply 10 processors. Then, as I mentioned, this part is the sequential part. So this part cannot be improved. So we can just improve this part. Okay. How much? Using the 10 processors, we can just, so this is the sequential part. So it's the same. And then for the parallelizable part, we can just the parallelizable part divided by 10, right? Then the total execution time is the 20 T add. So what is the speed up? Speed up is 110 divided by 20 is the 5.5. So if we use 10 processors, then what is our expectation? What is our expectation? So using 10 processors, we can expect that using these 10 processors, we can achieve 10 times 10 times of speed up. But the actual speed up for this workload is the 5.5. So this is the around this is 55% of potential. Potential is the 10. How about the 100 processors? So we can apply the same. So the total execution time is the 11T add, then speed up is just 10. So, and then using 100 processors, our expectation is that we can achieve 100 times of speed up, right? But actually for this workload, okay, 10 sum of 10 scalars and then 10 by 10 matrix sum, the speed up is just 10. So it's the 10% of potential. So it is because our workload, the target workload includes this amount of sequential part. And then this sequential part cannot be improved by parallel architectures. So this law explains the why why actually the performance of the parallel programs are limited by this sequential part of the target workload. Okay? And then let us assume that the matrix size is increased to 100 by 100. So for the single processor, the execution time is this amount. It's like this. And then 10 processors, we can just improve this part. This part is the parallelizable part, right? So the execution time is the 1010 multiplied by T add. Then what is the speed up? Speed up is the 9.9. It's around the 99% of potential. It is because using the 10 processors, our expectation is that we can achieve 10 times of speed up. So this is our potential. But for this workload, so like 100 by 100 matrix sum, then we can achieve 9.9. So 99% of the potential. So for the 100 process architecture, then we can achieve 91 is a speed up. So it is around the 91% of potential. So what does that mean? What is different? This workload and then this workload. But the speed up is different for the same parallel process architecture. What is changed? So it is because for the workload, this workload includes the large portion of parallelizable part. Right. The size of parallelizable part is increased. So what does that mean? In order to achieve higher speed up using parallel process architecture, then if we increase the fraction of parallelizable part, we can achieve higher speed up, right? Right? Do you understand? So it explains that for a parallel process architecture, then actually in order to achieve higher performance gain, then we need to increase the portion of parallelizable part. Okay, we can explain this using Amdahl's law. Okay, okay. So Amdahl's law explains only the parallelizable part can be improved by parallel process architecture. So which means the performance gain, the performance gain by parallel process architecture is limited by sequential part. Okay, so we can compare the strong and weak scaling. The weak strong scaling represented the problem size is fixed. Okay, so which means so this is the example of the strong scaling. So which means that the problem size is just fixed. Then we can just change the number of cores like this. Then we can calculate the speed up by parallel processor architecture. But we can also consider the weak scaling. The weak scaling means that if we just use the parallel process architecture, then we can also increase the problem size. So which means that the portion, the portion of parallelizable part. Okay. So this is the example. So it's the this is the some problem size. But if we just use the 100 processors, then we can also increase the problem size, so parallelizable part. Then we can achieve the same speed up. Okay, so this is the weak scheduling. So you may think that so this is not reasonable, right? So, but you can think like this. So Amdahl's law, Amdahl's law explains that actually the parallel processor is not good, right? Why? Actually, our applications include sequential part and parallel part, parallelizable part, right? But Amdahl's law explains the performance. The performance of our application is limited by the sequential part, right? So which explains that actually the parallel process architecture is not effective. It's not effective for increasing the performance of our applications. But problem is that the Amdahl's law assumes that the target problem size is fixed. But so when we utilize the parallel processor architecture, then we can just change the property of the target application. What does that mean? It means, oh, in order to utilize the parallel process architecture effectively, then we can also increase the size of parallelizable part. Right. So weak scaling just assume this approach. So which means the software can be changed. Okay. So we can just compare the strong scaling and weak scaling. Okay. Okay. So and then let's see some instruction and data. So we can classify the the CPU architecture based on the instruction and data. So actually this is called the Flynn Flynn's taxonomy. So taxonomy represents some classification criteria. Okay, so we can just uh, define the architecture of a CPU based on the some instruction and number of data handled by an instruction. So what does that mean? So we can just assume so instruction streams are single instruction and multiple instructions. And then we can also consider the data handled the 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 data handled by us on instructions. So for example, a single instruction can handle a single data. So this is the scalar instructions. So which means we learned about the add x1, x2, x3. So actually these register operands just includes single data. So each register includes single data, right? So this instruction, the add instruction just handle scalar data, right? So which means a single instruction handle single data, okay, scalar data. So this is called the single instruction and single data. So this is called the SISD, right? So this is the typical processor, typical uh, single core processor. So like the Intel Pentium 4. But using a single instruction can handle multiple data. So for example, single instruction like add dot v. So this is the vector add. Okay. So single add instruction can handle vector type data. Then what is the vector type data? Vector type data can include multiple elements like v1, v2, v3. So the instruction is single. So this single instruction handle multiple data. So single instruction, multiple data, it's called the SIMD. So SIMD is the vector type instructions. Okay. So for example, the x86 ISA, there are SSE instructions, and then these SSE instructions handle vector type data. So we can say that, oh, this is the SIMD type processors. Okay. And then multiple instruction and single data. So which means that the multiple instruction actually handle single scalar data, but no example today. So this is not efficient, right? And then MIMD. So MIMD is the multiple instruction and multiple data. So it represents the multi-thread, multi-threading. Okay, so which means that the multiple threads can be executed by multiple cores, or multiple threads can be executed using multi-threading. So this is the example of MIMD, the multi-core architecture, multiple instruction and multiple data. So this is called the Flynn's taxonomy. So and then so we can just classify CPU architectures using Flynn's taxonomy, such as SISD and then SIMD and then MIMD architecture. Okay. So as I mentioned, we can also consider the vector processor. So vector processor just handle the vector type data. Okay. The RISC-V also supports the vector extension, right? So RISC-V also support the vector extension. So the inner support the vector extension, then RISC-V can include the vector registers, the V0 and V31. So a single vector register can include multiple elements, right? So we can just implement the vector type instruction. Okay, so this is the example like FLD.v or FSD.v. So you can find the postfix v. Okay, so it's a vector type load and store, and then fed.v v. So this is the vector type add for the double precision addition. Okay, so we can just uh, implement some vector processors. So which means that using the vector processors, so we can execute the vector type instructions, right? So this is the example. So this is the conventional RISC-V code. So, and then this RISC-V code implement this operation. Okay. So y is ax plus y. Okay. So this is and the x and y are vectors. Okay. So using a conventional RISC-V code now to implement the vector type operation, then we need to utilize the for loop, right? So like the for I equal 0, and then I is less than n, and then I plus plus, and then we need to calculate the some y I equal a multiplied by x I plus y I. So this is the iteration loop. So as you can see in this assembly code, you can find this is the loop. What does it mean? So this code, the for addition is repeatedly executed by this RISC-V CPU. So this is the conventional code. But if we use the vector type RISC-V code, then we can just use the vector type addition. So like this. So fmo dot d dot bs and then fed dot d. So in this code, we cannot observe any iteration loop. So it is because this is we can just implement some vector multiplication or vector addition. Okay, so multiple elements can be executed concurrently by a single instruction, right? So this is an example. So actually, so we can also, so the modern processors includes so vector type instructions. For example, the Intel x86 includes the vector type instructions such as the MMX or SSE. And then actually, the multimedia applications includes the many vector type data. So actually using these vector processors, we can accelerate the performance of multimedia applications. Okay, so such as these applications includes the many vector type data. Okay, so okay, so SIMD. So also the vector processor also called SIMD. So as I mentioned, it's the single instruction and multiple data. And then and also these processors are called SIMD processors. Okay. Okay. And then so let's learn about the hardware multi-threading. So what is the multi-threading? So multi-threading means that in a single core, this is the single core, but this single core can run multiple threads concurrently. Okay, so these are thread. So this is the definition of multi-threading. So uh, actually, so we frequently find a CPU that supports multi-threading, right? So for example, you can find that, oh, this is the AMD CPU, but you can find that, oh, this AMD CPU includes 4 physical core and 8 logical core. So what does that mean? So using 4 physical cores, this AMD CPU can run 8 threads, 8 threads concurrently. So which means this AMD processor implements hardware multi-threading. Okay, so hardware multi-threading means that using a single core, so we can run multiple threads concurrently. So we can implement the multi-threading by using multiple registers. So it is because each thread includes its own registers, right? Like we can just assign registers x0 to x31 for this thread, also another x0 to x31 to another thread. Okay, so we require multiple registers. And because in order to run multiple threads, we need to require multiple program counters, right? Then we can switch between threads. So this is the hardware multi-threading. So we can also we can observe some different types of multi-threading, like the fine-grained multi-threading and then coarse-grained multi-threading. The fine-grained multi-threading means that we can switch threads after each clock. Okay, and then coarse-grained multi-threading means that we can switch thread only on long store, so like the cache misses. Okay, so this is the definition of a fine-grained multi-threading and coarse-grained multi-threading. Also, we can also observe define the SMT. This is the simultaneous multi-threading, SMT. So this is the example of the coarse-grained multi-threading and fine-grained multi-threading and then simultaneous multi-threading, SMT. So, and then this is the thread A, thread B, and thread C, and thread D. The coarse-grained multi-threading, so if thread A encounter cache miss, then there can be the very long pipeline stores, then we can switch thread, right? So this is the example of coarse-grained multi-threading. And fine-grained multi-threading, we can switch thread every clock. Okay, so you can find that this is thread A, thread B, and thread C, and thread D. So you can find that both threads are switched every clock. SMT, the simultaneous multi-threading, means actually the CPU can fetch the multiple instructions in a single clock. Okay, so this is called the superscalar. And the modern CPUs actually support superscalar, right? So SMT means that when we fetch instruction, we can fill the fetch slot from all thread. Okay. So in this example, this thread A includes the two instruction and thread B includes the 3 instruction for the the first cycle. So which means SMT just fill this instruction slash from two instructions from thread A and then two instructions and thread B. Okay, and then in the next cycle, then SMT fill the instruction slot using the one instruction from thread B and then three instructions from thread C. Okay, this is the simultaneous multi-threading. So actually, this is the hyper-threading in Intel. Okay, so there are the different types of multi-threading. Okay, so multi-threading means that so using a single core, so we can run the multiple thread concurrently. So which means in order to implement the hardware multi-threading, then we require multiple registers and then multiple program counters. Okay, so this is the multi-threading. So actually in chapter 6, I included the multiple topics, so more topics such as the GPUs or the interconnection network and the loop line model, but I will not explain about the GPUs and then other topics. So it is because so we can so it so actually these topics will be discussed in the graduate level course. Okay, like so actually the computer so I provide the GPU architecture course in a graduate level, right? So I will not explain about the GPUs and then interconnection networks and the loop line model. So in this course, okay. Okay, so in chapter 6, I explained about the parallel process architecture briefly. Okay, so the parallel process architecture so represent the multiple cores in a CPU. Then I explained about the parallel hardware and parallel software, right? And then I explained about the Amdahl's law. So Amdahl's law represent that. So the single application include sequential part and parallelizable part. And then using a parallel processor architecture, you can just improve the parallelizable part. So Amdahl's law explains the performance of the parallel architecture can be limited by the sequential part of the target workload. Okay, so I just showed the examples of Amdahl's law, right? And then I explained about the Flint's taxonomy. Like, so you can just explain the classes of CPU using instruction streams and data streams, right? And then I briefly explain about the vector processors and hardware multi-threading. Okay, so hardware multi-threading means that we can run multiple threads concurrently in a single core. Okay, this is the hardware multi-threading. Okay, so this is the end of this course. Then I will conclude this course. So in this course, we have explored the computer system architecture, right? So this the course name is the computer architecture. So we learned about the computer architecture at an abstraction level, and then we covered the performance in chapter 1, and then ISA instruction set architecture in chapter 2, and then arithmetic logic and hardware design in chapter 3. Then the process architecture. So actually, the process architecture is a pipelined architecture in chapter 4 and memory hierarchy, and then the brief explanation of parallel processor architecture. So this is the this is the undergraduate level computer architecture course, right? So these are uh, some concept, these are concepts covered by this course, right? But we did not learn about some advanced level of computer architecture, such as out-of-order process architecture, superscalar, branch prediction, cache coherence, memory consistency, blah blah blah, right? So, so these topics will be covered by advanced computer architecture course, okay, in graduate level, okay. Okay, so now you can explain which processor is better, Intel Pentium 4, Raspberry Pi 3, and then Intel Xeon, and then Intel i7, okay. So this is the server CPU, and then this is the personal CPU, and then Intel Xeon, and NVIDIA Tesla, right? So if you are interested, then you can watch the Turing lecture video. So actually, this Turing lecture was provided by the authors of the textbook, so David Patterson and John Hennessy. Okay, okay, so I'm work I'm working on the computer architecture research. Okay, so actually, I'm I'm working on the process architecture and the memory systems, then storage system, then also accelerate architecture. So if you are interested, then you can contact me, and then so we are hiring some graduate level students or the undergraduate interns. Okay, so if you are interested, then you can contact me. Okay, so this is the end of this course, and then okay, thank you for the effort for this course, and then your hardworking, you're hardworking for this course, and then good luck for the final exam. Thank you, everyone. Then good luck for the final exam, and then after the final exam, then enjoy the winter break. Okay, thank you guys, and then see you in the final exam. 감사합니다.